How do you evaluate if you have more than 2 sets of measurements from the same group? I'm Jacob from Intrepid Protoworks. Today, we are going to learn how to do the repeated measures one-way ANOVA. So, as the name implies, the repeated measures one-way ANOVA is a variant on the normal one-way ANOVA. So for all these introductory parts, the gamma function, the probability distribution function, the function get p from an f value, and the degrees of freedom between degrees of freedom within, all of that we're just going to speed through real quick. If you want to look at it in more detail, we have videos on each of those topics. We also have the code linked below. So we're going to go ahead and define our repeated measures one-way ANOVA function. It will take data and an alpha and get p, which we'll define as false. So to get started, we need to go ahead and get our number of subjects. To get that, we'll do the length of our data, then we'll do next iter our data dot values. So we're going to be taking a list again, and we want to get the size of one of the cells in that list. Then we want to get the number of conditions, which will just be the length of our data. So the number of lists in our dictionary. And then the total measurements will be the number of subjects times the number of conditions. So if we have 10 subjects and we measure them 3 times, that's 30 measurements. So now we're going to do the degrees of freedom. Our degrees of freedom between will be the number of conditions minus 1. Our degrees of freedom within will be our total measurements minus our number of conditions. Now, what makes this different is we split within into subjects and error. So our degrees of freedom for our subjects is the number of subjects minus 1, and our degrees of freedom error equals the degrees of freedom within minus the degrees of freedom for the subjects. And then our degrees of freedom total is our total measurements minus 1. With all that in place, we can start on our sums of squares. So we'll go ahead and define a few factors here. We'll do factor sum, total sum, and total sum square. Each of those is equal to 0. And then we'll loop through our data. We'll do 4 level values in data.items. Then we'll do level sum equals 0 for row and values going through the data in each level. We will then go ahead and add our row to our level sum, our total sum, and our total sum squared. Now we'll go ahead and back out of that loop. Then we'll go ahead and do factor sum plus equals our level sum squared. So between the above and our degrees of freedom, we can now start making our sums of squares. So our sums of squares between will be our factor sum divided by our number of subjects minus our total sum squared divided by our total measurements. Now our sums of squared within will equal our total sum squared minus our factor sum divided by our number of subjects. Next, we will need to get a sum of each of our subjects' measurements. So we need to sum up all the measurements for each subject. To do that, we'll make an empty list. We'll also make an iterator, and then we'll use a while loop. So we'll say while our iterator I is less than our number of subjects, our subject total equals 0, and then we'll do a for loop. So for level values in data.items, we will take the subject total and add to it the values I, so the place we are at in our list. And then we'll go ahead and back out of that for loop. It'll give us a total for a subject. We can go ahead and then add this value to our per subjects totals list. And we'll do that just by doing .append and subject total squared. We'll then go ahead and make ourselves a little bit more space. Go ahead and increment our I plus equals 1. And then we'll go ahead and back out of that loop and do our sum of per subject totals, which will be, we'll use the sum command this time, per subject totals list, and that'll give us a total of our per subject totals squared. And with that in place, we can do our sum of squares subjects. So our sum of squares subjects will be equal to the sum of per subject totals divided by the number of conditions minus the total sum squared divided by the total measurements. Now that we know our sums of squared subjects, we can get our sums of squared error, and this is the important one. So our sum of squared error will equal the sum squared within minus the sum of square subjects. And our total sums of squares will just be our sum square between plus our sums of square within. So now we have our degrees of freedom and our sums of squared. So let's go ahead and get our mean squares. So our mean square between will equal our sums of square between divided by our degrees of freedom between. And then our mean square error will equal our sum of square error divided by our degrees of freedom error. And then our f will be our mean square between divided by our mean squared error. So now the rest of this is pretty similar to the way we did our two-way ANOVA. So we'll make an empty variable, call it significance, and set it equal to false. Then if we decided to calculate our p, we will go ahead and print out calculating p, go through calculating p, and go ahead and report it just so we can see it. And lastly, we'll go ahead and set significance to true if our p-value is less than our alpha. And lastly, we'll just do a quick else statement to fill the p-value with something so that it can be printed out later on. Now with all that, we've got everything we need to start go ahead and build our model table. So we'll go ahead and say our model table is equal to an ordered dict because we want to maintain the order of our dictionary and we want to have labels. So we'll say our model table between is equal to our seam square between, our degrees of freedom between, our mean square between, our f, our p, and our significant. We'll do our model table within, which will have our sum squares and our df within, our model table subjects, which will have our sum square subjects and our df subjects, our model table error, which will have our sums of square error, our degrees of freedom error, and our mean squared error, and then we'll have our model table total, which will have our sum square total and degrees of freedom total. Lastly, we'll go ahead and return our model table and our df error, returning df error just to make it a little bit more simple later on. Make ourselves some more space, and let's go ahead and actually start experimenting with some data. So we're going to go ahead and build a empty ordered dict that'll be similar to what we've done before, except this time we're going to simulate a set of classes. So we'll do our data set equals ordered dict, our data set before, 1 class, 2 classes, and 3 classes. We'll then go ahead and open up our data set that we've been working with the entire time, go through all the standard filtering that we do. We're going to go ahead and filter out and just look at an income range. So people making say $20,000 to $80,000 or something to that effect, or whatever you want to put in here. We're just doing it to make the effect stand out a little bit more. And then we'll go ahead and append incomes to each one of these. So before we append them, we're going to go ahead and also add a random value to it. So we'll say that each class increases it by some amount. The amount for our example doesn't matter a whole lot. We'll just put in some amounts here, and that will give us our data set to work with. And then we'll go ahead and resample from our data set for a specific cell size. Cell sizes are absolutely necessary to be the same because if they're different, that means you have something wrong with the number of subjects you have. So this time we'll go ahead and name our cell size just num subjects, and then we'll go ahead and sample from each of the lists in our ordered dictionary above. This will also be the same as in previous tutorials. So if you want more detail on how we did it or how we do this and why you do it this way, go ahead and look back at some of the previous tutorials. Also, like previous tutorials, we'll set our alpha equal to 0.05 and our get p equal to false to start out. Then we'll say our results and our degrees from error equals, well, let's see, go ahead and grab our function real quick. Our repeated measures OneWAY ANOVA, and I'll take our data sample, our alpha, and our get p. So now we have our results. So we're going to go ahead and format our header, go through, loop through each part of our model, print it out. We've done this in a previous tutorial, so we're going to speed through this really fast. It's a little bit different than before, but by and large, we're doing the exact same thing as we've done before. If you need to pause, go ahead and pause, or you can also just reference the code on the GitHub. We started using string formatting like this in our two-way ANOVA tutorial. So with all of our results printed out, we can also do, if it's significant or not, we'll go ahead and make some more space and print out our means. That way we can get a little bit of a visual representation of what's going on. To that, we'll import matplotlib.plt or .pyplot as PLT, and then we'll go ahead and use style BMH. You can print out styles. We've done this before in our charts tutorial. Go ahead and make some empty lists, and that will let us build our graph from our dictionary. So we'll say for key data in data sample.items. We'll say our labels is equal to our key, or we'll append our key to our labels. We'll append means by getting mean for our data. Our positions will just append I, and then we'll increment I at the end, and that should give us all the information to make a graph. So we'll do plt. bar. Positions means we'll say our color of our bar graph is gray. The width of our bars will be 0.5. Our alignment will be centered. And then we'll go ahead and do our error color. We're not using error bars in this place, but I like to keep it here anyways. We'll do that as black, and then our cap size, again, we're not using error bars, will be 5. And I'll do PLT X label. We'll say sample incomes. We'll do PLT.Y label, and we'll say sample income or mean income in dollars. Then we'll do PLT.title, and we'll say awesome class from, or awesome incomes for make lots of money classes. Then we'll go ahead and do PLT.xticks, and that'll be positions and labels. And then we'll do PLT.show. With all that done, we are ready to save and run our data. Let's do it in a new dedicated console. This will take a minute to run, and it'll take even longer. It looks like we do have a typo. We just capitalized total sum on accident. So let's save and run again. So this time we got output. So let's go ahead and stretch this out and bring our graph back in. And it looks about like what we should be expecting. So let's run again just for seeing it again. All right. And we'll just go ahead and run this a couple of times to make sure everything looks right. Some of the things we're looking for to make sure are, now we're not getting any negative values, like we shouldn't be getting a negative sum of squares for any reason. And also just make sure that everything makes sense with our simulated data set. And now let's go ahead and set our get p equal to true. And remember, this will take a long time to calculate, or it could take a long time to calculate. So get up and make yourself a cup of coffee or something like that if you're following along with this tutorial. If you're using your own data set and you get something like a value error, or you get something like an overflow error or something similar, it could be that your degrees of freedom is too large, which means you need to put some kind of stop for that so that your calculation will still work. Chances are, if your degrees of freedom is that big, then having it be a little bit bigger won't matter much. Now, if you are finding the p-value to be problematic for some reason, then you can also still take your F ratio and reference a table. So we have our results. We can see that now that we're getting a p-value, it will give us an interpretation of that. So for repeated measures in ANOVA, the results are significant where alpha equals 0.05 and F, degrees of freedom between and within, is significant at our F value and our p value. Now that about does it for our repeated measures one-way ANOVA. Our next tutorial will go over the two-way ANOVA mixed measures. So we'll have one factor be the repeated measures factor, and we'll have one be an independent measures factor. If you have any questions or comments or thoughts, please leave them down below. We're getting really close to the end of this series, so if there's any tools you'd like to see covered, make sure to say something in the comments. And don't forget to like and subscribe.